Okay, number 6 has tennis ball hitting the ground. Given the speed, direction, we want to find its speed and direction after it bounces. Coefficient of restitution is given, so it's not perfectly elastic. We have some energy loss. Don't assume that this is like a homework problem. We had a homework problem with an incline. Not sure why I did that. Let me get back to where I was. Let's see. We had a homework problem with an incline. This one is actually hitting the ground. So there's our ground. We'll draw our tennis ball right the instant before it hits. It's got a speed going downward, 10 meters per second at an angle of 30 degrees relative to horizontal. Okay, we want to find its velocity after it bounces. Okay, so this velocity is going to have some angle and some magnitude, v prime. Now, if you remember talking about collisions, we had, for this type of collision where we have a coefficient of restitution given right here, we had to define the line of impact and the plane of contact. So, plane of contact is the ground. Okay, perpendicular to that is our line of impact. Okay, and when we developed our coefficient of restitution, we said that the velocity along the line of impact, so let's call this x and y, the velocity along, let's do the plane of contact first. The velocity along the plane of contact is going to be unchanged. So Vx is going to be Vx prime along the plane of contact. Along the line of impact, we used our coefficient of restitution equation. Alright, so we said in general E is the final velocities difference, and let's see, let's write this correct, V1 prime, and that's going to be a negative, and it is, just referring back to my equation sheet, V2 minus V1. Okay, so this is line of impact, so all these would be y's in our two-dimensional case. Alright, so from this we can say that 0.6 is equal to negative. Let's call object 1 the ground and object 2 the ball. Alright, so the ball's y velocity after impact is what we're trying to find. Velocity of the ground after impact is 0. Okay, object 2's velocity before is, I'll just write it as v2y, and again this velocity of the ground is 0. Alright, so we look over here, there's a velocity before. If we break it into two components, I'll do that over here. So I have 10, I'll have 10, this angle's 30, so 10 sine of 30 in the negative direction is my y velocity. Let's see, let's cheat a little bit and drag that over to give us some room. So that's a negative, and then in the x direction it's 10 cosine 30. I'm just breaking our velocity into two components. Alright, so using that we get v2y prime is equal to, so I'm solving for this, so I'm going to multiply by the negative and the v2y, so it's going to be a minus 0.6, and then v2y, so this is v2y before the collision, minus 10 sine 30. Sine of 30 is 1/2. So half of 10 is 5. 0.6 times 5 is 3. And that'll be units of meters per second. Double check to make sure I did that right. Looks good. So that's the y component of the ball after the collision. We've already said the x component after the collision is going to be the same. Just for consistencies, we'll put 2's on these, okay, because that's what's moving. And so v2x prime is going to be v2x is going to be 10 cosine 30. Okay, that number comes out to be 8.66, I believe, but I'm going to double check. 10 cosine 30. 8.66. Again, meters per second. Okay, so just redrawing it over here, we've got an x component of 8.66, a y component of 3. We're looking for that velocity and that angle. Square root of sum of the squares. 8.66 squared plus 3 squared. It's going to give me that quantity squared plus 3 squared, square root. 9.16, 9.17 rounded. Meters per second is the magnitude, and tangent theta is equal to 3 over 8.66. Theta is equal to inverse tangent 3 divided by 8.66, 19.1 degrees. Okay, so final answer 9.17 meters per second at an angle of 19.1 degrees.